All right, so for this video, I just wanted to take a little bit of time to focus on the math work that goes with this chapter. This chapter only has two formulas that we're asking you to be responsible for today, and hopefully you'll find that they're both very, very simple formulas to manipulate, okay? So let's get started with just kind of reviewing that we are talking about waves. Waves carry energy. We are focusing on electromagnetic waves where the waves do not require a medium. And we talked about the wave speed, that the speed with which a wave passes through a medium is going to depend upon the medium in which it travels. So what in the world does that mean? That means that I have a beam of light, but that beam of light is going to move faster passing through some materials than it does through others. And the biggest reason for that is because of the density of those materials. If you don't remember what density means, this is a term where we're talking about basically how crowded, how packed in are those molecules. So electromagnetic waves do not require matter. I want you to think of the light as passing through that space in between the atoms. So if we have a material that's really, really dense, aka thick, okay, something where the molecules are really packed in tight, well, it's going to be very difficult for that light wave to maneuver through the space in between because there's not a lot of space in between. And so as a result of that, it's going to have to slow down to make its way through that material. So less dense materials, light is going to travel faster because there's less things that it has to maneuver around, so it can kind of just move about its business at pretty close to its normal or full speed. So that's kind of the gist behind understanding how the different materials or mediums are going to affect our light speed, okay? So whenever we're talking about calculating the light speed, in general, all waves, and we covered this in the previous week's lesson, all waves are calculated by taking the frequency of that wave and multiplying it by the wavelength. So frequency times wavelength gives us the speed of our wave. In this particular chapter, we are focusing on electromagnetic waves. Well, I will go ahead and tell you all electromagnetic waves will have a speed of 3 times 10 to the 8th meters per second. So what does that mean? That simply means that as we are filling in our numbers for our frequency and our wavelength, if we have a really big number here for frequency, inversely, we'll have a small number for our wavelength because together they are going to equal this set value, which we will use the letter C to indicate that set value, and that will be the number 3 times 10 to the 8th, okay? If you are being asked to calculate any type of, whether it's a frequency or the wavelength or whatever, and we're talking about an electromagnetic wave, that C value is 3 times 10 to the 8th. It's a radio wave, it's a microwave, it's a gamma ray, it's visible light, it's blue light, it's red light, it doesn't matter. They all travel at a value of 3 times 10 to the 8th meters per second. That's what the speed of light is, okay? All right, so as we get into the math, we're going to have to make sure that we're understanding the difference in the use of the words that we're going to read. Some of them are going to be just minor differences, but it will affect the meaning of what it's asking us to solve for and how we're going to plug our numbers in, okay? So just to review, hopefully you've already done the notes where we're just talking about some basics on waves. And so in those notes, we talked about the fact that light is going to travel fastest in a vacuum, where there are no particles to get in its way. So if we were to have, if there was a radar gun that could actually track the speed of a beam of light, let's say that we had a radar gun that would do that, which we don't. But if we did, let's say that it tracked every single beam of electromagnetic light or electromagnetic waves at 3 times 10 to the 8th if we were in outer space, okay? If we then had that light passing through some other type of material, although we know it can travel as fast as 3 times 10 to the 8th, it may not quite read that high of a speed. So we need you to know conceptually the fastest it can travel would be through a vacuum or space or outer space, and so this would be its true speed, that value of C, 3 times 10 to the 8th. if we're talking about light passing through a medium such as air, it actually travels pretty much as fast as its true speed. The density of air is so small that it doesn't really affect the speed with which light travels. So right now, wherever you are, outside and there's sunlight shining down at you, or you're in your house and there's a room light on, the light is traveling to you at a speed of 3 times 10 to the 8th meters per second right now to get from its light source to you, okay? Traveling through that air around you. All right, so when we get ready to do our math work, this is our formula for the speed of the wave for this chapter, because all of our waves are going to be electromagnetic waves. So again, visible light, obviously, but then this is also going to include your gamma rays, your microwaves, your radio waves. All of those waves are going to have a speed of c, okay? All right. We talked a little bit about some of the different wave behaviors, and we talked about how there's reflection and there's refraction. Make sure that you know the difference between the two, but let's focus on refraction for just a moment. When we're talking about this beam of light that we initially had that was coming in right here, if it does not change materials, that beam of light should follow this path. This was the original path that it was on, right? But if that light passes into a different material, the density of that material, the thickness of that material is going to affect the speed. So more dense materials are going to slow down our beam of light. So instead of the light passing and landing over here as it was originally moving, instead that beam of light, once it hits this boundary, slows down and ends up over here. You can see closer to that imaginary normal line that we're using to measure all of our angles. So when we talk about the density of the material, yes, we do have density values, but when we're calculating how the speed of the wave is manipulated or the path is manipulated, we're actually not using the value for density. We're using something called the index of refraction. And so the index of refraction is going to tell us how dense our material is based off of that value. Now, you are also being asked to know this word right here called the critical angle. And so the critical angle is basically the point at which our light stops reflecting and starts refracting. Or it's actually probably better to say it's the point at which it stops refracting and it bends so much that it begins to just bounce back and reflect, okay? So I don't want to elaborate on this too much right now because the focus of this video is the math work, but if you guys will go to my Google site, go to Google and search Miss Espinosa Physics, there is a video. The top 4 videos are going to be most helpful for this chapter. So there is a video that's talking about refraction, and they discuss the critical angle and what that is, but to sum it up, it's that point where the light stops refracting and begins reflecting off of a surface, okay? All right, so let's get into the math for this index of refraction. So the letter N is going to represent our index of refraction, and so basically this is a way of telling us how dense that material it is, and because we know density is going to affect the speed, that's exactly what this is giving us. The N value basically is a ratio. How fast the light should be moving through a vacuum. So this would be light's true speed, right, in an ideal situation, and how fast the light is moving because of the density of that medium. So this would be like its actual speed. So the ratio between how fast light is supposed to move and how fast light is actually moving because of that denser material, that ratio is going to give us that N value, okay? So both of these units are going to be meters per second, so your N value is actually not going to have a unit. So we can see from this example here, air has an N value of 1, as I stated before. It really does not disrupt the speed. So if we were to do the math work for the N value for air, the actual speed that the light travels through air would be 3 times 10 to the 8th. And then the speed light is supposed to travel through a vacuum is 3 times 10 to the 8th. So that reduces to the number 1. So N has, the N value for air is the value of 1. Here you can see we have an N value for glass. Now we all know glass is more dense. Because it's more dense, the light is going to slow down. So when we do the math work for this ratio, and I don't know the actual speed, but this is 3 times 10 to the 8th, and then this speed is going to be some number less than 3 times 10 to the 8th. So whenever I do my math here, I end up with some number 1 point something, right? It's not a perfect 1-to-1 ratio. And so that's the gist behind how the N values are helpful. All right, so all I want to do now is just work a few practice problems with you. Okay, so let's look at example number 1. It says light travels through a liquid at 2.45 times 10 to the 8th meters per second. What is the index of the liquid? So they are asking us to solve for N. Okay, so if we're going through the guess process, this is a V. This is not C. C is always 3 times 10 to the 8th. This is a V. This is the speed that the light is actually traveling through that medium. And they're asking me for my N value. So if you look at your formulas, you only have the letter N available right there in that formula. So that is the equation we will use. N equals C over V. Now we don't have C on the list, but you should know by now that that's a set number. So 3 times 10 to the 8th meters per second. So in order to solve this question, it's real simple. 3 times 10 to the 8th over 2.45 times 10 to the 8th. And you put that in your calculator. And we get 1.22448, blah, blah, blah. Okay, of course, we're going to round this for sig figs. So my N value would be 1.22. Guys, your N value should always be 1 point something. If you get anything less than 1, you messed up. If you get some really crazy big number, you messed up. Okay, all right. Bruce Banner is hit by a gamma ray with a wavelength of... Let's go with green for the Hulk, right? With a wavelength of 6.37 times 10 to the negative 13 meters. What is the frequency of the gamma ray? So we're given a wavelength of 6.37 times 10 to the negative 13 meters. And they are asking for the frequency. Okay, again, looking at our formulas, frequency is in this equation right here, and they gave us the wavelength and they're asking for the speed. So that is obviously the formula that we're going to be using. So V is equal to F lambda. Now for this particular chapter, this V really should be the letter C, right? So let's go and change that. This should be the letter C. So C is equal to F lambda. All right, so then now we're going to plug in our numbers. 3 times 10 to the 8th equals F is our unknown times 6.37 times 10 to the negative 13, and then we're just going to divide by that. Okay, so that'll cancel. So 3 times 10 to the 8th divided by 6.37 times 10 to the negative 13 gives me 4 points, and I'm going to go ahead and round this for sig figs, 71 times 10 to the 20th. And what do we measure frequency in? We measure that in hertz. Okay. All right, last example. Let's get us a different color here. All right, so it says light travels through a medium with a refractive index of 1.39. So this is the letter N. So I know that because it calls it the refractive index. I know that because there's no unit at the end of this number. What is the speed of light through which, the speed of light through the refractive medium? So guys, this question is not asking for the letter C. It's not asking for the speed of light for electromagnetic waves. It is asking for the speed specifically through this medium. So they are asking us to solve for V here, okay? So since we have already established that this first formula up here on the slide is really C equals F lambda, that is not our formula to use for this particular question. Here is where we have our V for velocity that they're asking us to solve for. So N is equal to C over V. And once again, we know what the value is for C. So we're going to plug our numbers in. 1.39 equals 3 times 10 to the 8th over V. If you don't recall the shortcut, here's a quick review. This and this trade places. V is equal to 3 times 10 to the 8th over 1.39. And that gives me, and once again, I'm going to go ahead and round this for sig figs, 2.16 times 10 to the 8th meters per second. So if we look at this answer, 2.16 times 10 to the 8th meters per second is indeed slower than the true value of the speed of light, which is 3 times 10 to the 8th. This makes sense because it's passing through a more dense material, because we can see I have an N value greater than 1. Okay? All right, well, I just wanted to take a little bit of time to kind of go over some math questions for you. And you guys have a little bit of practice work to do. Hopefully everything will be pretty straightforward. The formulas that you have for this chapter are just these two equations that you see on the screen. All right, I will talk to you guys soon.